Yes. Good afternoon, everybody. It's my pleasure to talk here and also present the work here. And already you had a short introduction about me. So I'm here at the NTNU, at the Norwegian University of Science and Technology. We actively recruit PhD and the postdoc here, and of course, faculty member as well. And we welcome a researcher from all over the world. And we go through a very good procedure of hiring, try to have a balance regardless of the origin and all the things. So we welcome everyone, and we always have some PhD and postdoc position open, and the PhD and postdoc are considered as an employee here in our department at the NTNU. They are temporary employees since they are hired for a fixed duration of time. For example, the PhD is hired for 3 to 4 years, depending on whether they would need to have some teaching duties or other duties. If they have some duties, then it will be for 4 years. Otherwise, it is for 3 years. And they get all the benefits as other professor or the permanent employee of the department. And it's also same for a postdoc. And what we look mainly for is the motivation, whether the candidate could successfully finish the PhD in time. So that is one of the main factors that we actively look when we hire a student. And also, of course, we check the experience. Does the candidate has the relevant experience that we are looking for? So the PhD and postdoc are for a particular project, and project has its own objectives and research goal milestone. So we look for a candidate who can carry out the research and achieve the goal. So that is very important for us when we select. And of course, after the initial checking, we make a short list and then invite some candidate for an interview. And we hire one of them. And of course, we also talk to their supervisor or some reference person to know about the candidate more. So that's the last step of the process. And then finally, we give the offer. So I'd also like to say about our department. Our department is not a very big department, but is growing fast. I think in our department, we have maybe more than 100 temporary and the permanent employee, maybe around 30 professor, associate professor in our department. And in our department, the research group is divided into 5 research groups. I'm just opening the website to say the name of this research group. And the first one is the electrical machine and the electromagnetics. So they focus on the machine design for any application, including aviation and industrial motor design. And the second one is the electricity market and energy system planning. So they focus on how we can integrate the renewable energy and all other emerging energy into the system effectively. So they focus on the market policy. And the next one is the high voltage technology. So they focus on all high voltage technology, including high voltage cable, high voltage transmission, insulation, all these things. And the next one is the power electronics system and the component, and I belongs to that group. In our group, we focus on the power electronics from component level to control level up to primary, secondary, tertiary control, microgrid control, smart grid control, all the things. And from the device level, one of our professors also focus on the wide bandgap devices, for example. And you might heard about one well-known professor in power electronics, Ture Ondelen, and he has a very famous book on power electronics. It's a textbook. So he's from our department. And yes, so we actively focus on power electronics for many applications, including renewable energy integration, solar, wind, energy storage, electric vehicle, high voltage direct transmission system, fax devices. So all the things that we focus in our group. And then the last one is the power system operation and the operation and analysis group. So these are the 5 groups that we have in our department. And I put the link of our department, and then if you are interested, you can go through more detail about the. Hello?
Yes, yes. Thank you. Thank you, Dr. Amin.
I do not see the window. Then
Yes, yes, please.
I'm just checking the window that since I should see the window, right?
Hi, I'm Brett Callen, and in this video, I'm going to show you how anyone
Sir, you can share your screen, sir.
Just like the one you're watching right now, using Doodly, our drag and drop tool software that allows anyone, regardless of tech skills, to create highly engaging professional doodle videos in a matter of minutes.
Okay, yeah, I found it. Yes, since I'm new actually with this Google Meet and we use other platforms, so.
Doodly is now the video tool of choice for.
And I put the link of our department here in the chat window, and we can see more details here.
Perfect for marketing.
And also, I'm putting the
and even inspiring others.
Where we advertise all the opening, position opening, the chat window. Maybe some of you find some
great doodle videos
listing position, then you can actively look at, and if you find something that meets your expertise, then you can also apply here. So that's a short introduction about our department. And of course, we have a very good overview about the NTNU. I'm not going more detail presenting about the NTNU. Now maybe it's time for start with the presentation.
Yes. Thank you, Dr. Amin. Yeah, can you please share your PPT and so that you can start your presentation?
Yes. Shall I share the PPT or shall I share the screen here?
Yeah, you can click on present now, sir.
Right side, you see right side bottom.
I think yes. My screen is
now you are sharing.
Now it is visible. Now you can.
Okay, now my screen is visible.
Yes, very much good.
Yes, thank you. Then maybe I can start with the. Hello everyone, welcome to this presentation. It's my pleasure to present the topic here. The title of this topic is Integration of Wind Power and Focusing on Stability and Interaction Issues in Integrating Wind Power. This is the main outline of this presentation. I will first talk about a brief overview about the wind power system and present status of the wind power. Then I will present some stability and interaction analysis, the methods and tools, how we can analyze the stability, and some possible solution to overcome this interaction. And finally, I will conclude this presentation. We know that power systems are going through a paradigm shift. For example, if you see the figure, this is a traditional power system where we have the mainly synchronous generator-based power generating unit, like coal, nuclear, or hydropower, and we have the industrial and the residential load. But if we look at the future power grid, it's look a bit more complex. In addition to this traditional generator, and we have many other components in the grid, like wind power. The wind power, they can be directly connected to the grid, or they can be connected to the high voltage direct current transmission system. And in addition, we also have some other player like solar, energy storage, electric vehicle, and it's also have you can also have the smart home, and they can be connected through power electronics. So in future grid, we are expecting many power electronics based system in the grid. So this is more like how a future grid look like. And if you see the present, the global electricity production, and still the main generating unit is the synchronous generator based unit, like the nuclear, coal, and the other unit, and the renewable energy is increasing. And the major share of the renewable energy for now is the hydropower. And we see that hydropower is a kind of saturated, it's not increasing that much over the years, but it's still increasing. The major other two renewable energy is the wind power and the solar power. They are increasing tremendously. So far, up to 2019, we see that it's around 6% wind power integrated in the global energy, and the 2.8% solar power integrated in the global energy system. And they are increasing. And if we look at for the wind power, and you can see it's increasing over the years. For example, last year is around 60 gigawatt added to the global energy system. And if you see the current share of the renewable energy is current share of the wind energy is around 650 gigawatt. So this is a lot actually. And we still need to integrate more renewable energy if we want to have 100% renewable energy in the system. And where this renewable energy, the wind energy are located, they usually, these wind farms are located where we have the steady and high speed wind, which are usually far from the electrical grid or the load. For example, here I put two examples. One is for the Texas Panhandle. It's one of the largest wind farm in the US. And they are far from the main Texas grid. So we need a very long transmission line to connect this wind power to the grid. And if we look at in the Europe, and in the Europe is a North Sea region has a good wind speed. So offshore wind power is developing in the North Sea region. So this is the figure of the North Sea. And I showed some plan and installed wind power system in the North Sea region. And here we can see some of the wind power. They are connected through mainly high voltage direct current transmission system. And here this is Norway and England. And we also have some high voltage direct current transmission system. For example, this Skagerrak transmission system, we have initially it's a LCC based transmission system. Now we have also voltage source converter based transmission system. So the plan is to integrate, connect different grid, different countries through high voltage direct current transmission system. So we have the wind power in the North Sea region, and we have also offshore load. And this is an oil and gas platform, and the plan is to connect them here so that this wind power also can supply power to this offshore load. And if you see in the global, Europe is leading the way in interconnecting offshore wind via high voltage static current transmission, with a few operational projects in the North Sea. Borwind is one of them. Borwind 1 is one of the most remote offshore wind farm cluster in the world, connected to German grid by a 400 megawatt, 150 kV high voltage direct current transmission system. So several others also coming, already integrated also, like Borwind 2, Tailwind 1. So many different in the Europe actually. And if you see in the US, the first US offshore wind farm is the Block Island, was installed recently of the Rhode Island coast. With a cable connection to the shore, this 30 megawatt offshore wind project feature 5-6 megawatt turbine. So this was a bit a smaller system there they installed, but gradually they are increasing. Further, SBDC offshore installation are planned along the US East Coast, so that they can transfer more amount of power from the wind power system. And the largest clean energy transmission project in the United States was the wind energy produced in Oklahoma wind's windy Panhandle region to the Memphis, Tennessee area. From there, it would be distributed by the Tennessee Valley Authority to other major power distribution system in South and Southeast. So it's a very long distance that they plan to transmit power from this wind power system. So there are many happening in the US, in the Europe, and also I think many things happening in India, in China. China is also one of the leading in installing renewable energy, both the solar and the wind. I did not include it example here, but we know that they're integrating, they're coming a lot of wind energy, both in the Europe, both in China and India, in Asia. So how they are connected actually? If we have the wind turbine generator, and we know that wind speed is not constant, and the power generated from the wind, it depends on the wind speed. So since the speed is not constant, one of the way of integrating is a variable speed operation, and use the processor here. So what it does, it has the variable frequency voltage, the AC power, and it process and connect to the grid. So this is the one way of connecting wind power to the grid. And the grid, it could be 50 or 60 hertz. For example, we know that most of the Asia and Europe, it is 50 hertz, and in the US and part of the Japan, it is 60 hertz. So we have the power processor here, and that allow to integrate the power to the grid. So if we look at the technology, wind power, there were different technology, type 1 to type 4. Here in the figure I'm presenting is the type 4, where we have the full power back-to-back connection. So what it does, it has the wind power, and you have the generator, mostly permanent magnet synchronous generator, and that produces the power. And you have one rectifier here. So this is a power electronics converter, and it rectified and also operate with the maximum power operating point, and generate here DC power. And then we use another inverter and connecting to the grid through a filter here to remove the high frequency component. So this is now the mostly used wind energy conversion system topology. Another very popular topology is the double fed induction generator based. Here, this is a double fed induction generator, and is connected through the grid, and the rotor is fed through power electronic system. So we have the back-to-back power electronics converter, and connecting this double fed induction generator to the grid. So these two are, the first one is called the type 4 and the second one is called the type 3. These are the most popular wind energy conversion system that is widely used now in modern wind power system. And what about the converter topology used in this wind energy conversion system? We know that there are many different types of converter topology. Two-level, for example, this is a two-level voltage source converter, three-level voltage source converter. It also could be a multi-level converter now used for this converter here. But these are the most popular topology that is used in the wind energy conversion system. So these are the power reference converter, and it needs the controller to turn on and off these semiconductor switches. And they could be MOSFET, IGBT, or other semiconductor devices that we used here. And now if we look at the topology, in power layout, there could be many different types of layout. Mainly three layout are used, like AC-AC layout, and DC-DC layout, or DC-AC layout. So what we see in the wind farm, we see that wind farm consists of a number of elements like wind turbines, local wind turbine grid. So we have a lot of wind turbines and local wind turbine grid, and collecting point, and transmission system. Then wind power interface to the point of common coupling. And it shall be noticed that all wind turbines here are voltage adjusting units. That is, we have the AC to DC transformer here, this AC to DC conversion topology. So this example here is a AC-AC layout. This means it's connecting the AC. We have the AC and then we are converting to AC here. So it's a AC-AC layout. It's also possible to have that this DC, we have the wind power here, each of the unit like back-to-back converter, and this DC bus can be connected in series or in parallel. So then we collect all the DC at a and then finally with a big power level converter, we connect it to convert them to AC. So there are different configuration, different layout possible. For example, now here in this rest of the analysis that I'll present, I'll consider that they are AC-AC layout configuration. So we have the wind power, and then if it's an offshore wind, it's an onshore wind power, then we use a long transmission line, AC transmission line, to connect to the grid. So it's also possible that we know that we install the wind farm where we have the steady and high wind speed, and they could also be located in the offshore. Also, they are far from the main grid. So I start with here. If they are sorry, if they are far from the main grid, then we need a long transmission line. And if they're in offshore, then the transmission distance could be several hundred kilometers. So for a long distance, it's not easy to transmit the power over a long distance, especially for an offshore condition. Since we know that in offshore, we need to use the transmission cable. And when you have the cable, and after certain distance, for example, here, this one is power level. If we have this red dot dashed line, is for the power transfer over through the cable. And we see that when the transmission distance, if longer than 50 kilometers, then we are not able to transmit power anymore. So it's for the AC transmission line, this one. When if we have a high voltage direct current transmission system, even in offshore transmission system in the sea, we can still transmit power over a long distance. several hundred kilometers. So this is one of the big advantage integrating wind power, offshore wind power, of course, through the transmission line, high voltage transmission line. Another thing is that if we have to transmit the power over a long distance, and we see that after certain distance, we can say this is the total cost for this pink color is the total cost for AC transmission system, and the green one is for the high voltage direct current transmission system. If the transmission distance is higher than a particular length, several hundred kilometers here, and the cost, installation, investment, all the cost is much higher for the AC transmission system. So it's better to go with the high voltage direct current transmission system. So we see that even if we have the longer transmission system, and it's due to the advancement of the power electronics topology, the converter and the devices, we can integrate the wind power even if they are located far from the main grid. So that is one of the advantage. And also other advantage that bring by the high voltage direct current transmission system is the asynchronous system. If the two systems, even they have the different frequency, but still we can use the high voltage direct current transmission system to integrate the two systems. So now we have the high voltage direct current transmission system, and of course they are the power electronics converter. There are different converter topology that we use to integrate the transmission system. And if we look at the converter topology for a high voltage direct current transmission system, when they are installed initially, and those are mainly line commutated converter based on the thyristor. And we know that when we use the thyristor, then it needs a lot of filtering element, and the reactive power injection is only one direction. This means thyristor consume a lot of reactive power, and we need a lot of filter here with the LCC converter. But due to the development of the other topology, like a voltage source converter, 2-level, 3-level, and they can have the bidirectional power flow control using, mainly the reactive power. So filtering element reduce a lot compared to this LCC. And recently, another converter is called the modular multi-level converter. This brings many more advantages. It reduced the ease of filter a lot, since we have the multi-level. We can generate the sinusoidal voltage with the many level that reduce the requirement of the filter. So those are the main converter topology now used in modern high voltage direct current transmission system. And this modular multi-level converter is gaining popularity, and now most of them using modular multi-level converter in high voltage direct current transmission system. So this is the some overview about the wind power integration. Now I want to show some challenges. First, I start with this one. And if we want to have more renewable energy, and we see that the hydropower, they are now a kind of saturated, so we need to go through mainly the wind power and the solar power. And the both wind power and the solar power, they are integrated through high voltage direct current, through power electronics converter. And since the power electronics converter, they are controlled by the control algorithm, they are very fast. Their dynamic is very fast, and also we know that this renewable energy, they are the output power of this renewable energy depend on their like wind speed or solar irradiation. So they cannot inject power all the time. So there's a larger variability in intermittency nature, and it introduces more uncertainty. And of course, it also increased the flexibility since the traditional power system, it flows one directional, but now we are integrating this renewable energy also in the distribution transmission system. So it's also increasing the complexity in the distributed system operator or the transmission system operator to manage all the complex network. So these are some challenges it brings. And since they are very fast and we have less time to take action. For example, if you have the synchronous generator and they have inertia, and it gives much more time to take action to prevent any fault or anything happen in the power system. But now the power electronics, they are very fast. So that brings some complexity. So this is about the traditional power system I presented, and we see that how the traditional generator works, the synchronous generator, and they are working for more than 100 years with maintaining the synchronization. So they works as expected and support the grid by regulating the voltage and frequency. So how they regulate the voltage and frequency? If you look at to the synchronous generator block diagram, then we see that it has one governor, and we give some reference power, and it compared the frequency of the grid. By comparing the frequency, then it generates power, so it regulates the frequency of the system. That's what synchronous generator does, and also it regulates the voltage by regulating the reactive power. So you have the excitation system, and you set the reference voltage some point in the generator terminal or maybe far from the generator terminal by impedance compensation, and it regulates the voltage. So it regulates both the frequency and the voltage by means of regulating the active and the reactive power. We have this relationship between the power frequency. If it operates somewhere here for a synchronous generator, and when the load increase, then it decrease the frequency. It has the three level of the controller: primary, secondary, and the tertiary. In the primary control, it acts instantly when there's a change of the voltage and the frequency. So it acts based on the power frequency relationship. So that we have the power frequency relationship installed here, and the voltage reactive power relationship. So that is it's always regulate the voltage and frequency in its terminal in the system. So they operate as expected. But what about if you go for the renewable energy? Here our focus is the wind power, and if we see for the full power back-to-back wind energy conversion system, and what we see that the output power of the of the wind generating unit depends on the speed of the wind. So if we have the we cannot get higher or the lower power, then we can get the lower power if we set, but we cannot get higher than the power getting from the wind. So that is one of the limitations, that it cannot always control the frequency. It cannot change it operating. For example, when the frequency drop due to the increase of the load, the wind power cannot send more power because the power is limited by the wind speed, the power generating from the wind. So that is the big problem here we see. And another things, it has a controller and many cascaded controller in many cascaded controller here. For example, this is one of the standard control system that you use to control the converter. Like we have the inner loop current controller, we have the outer loop voltage controller or the reactive power controller, and in addition, we need also a synchronization unit. So we have the many things, and also we have the intermittency nature of the renewable energy. So that is the one thing that we see here. And when we want to integrate the wind power through high voltage transmission system, and the system is even more complex. So what we see here, each of them are representing wind farm, many wind turbine generator together here, and we see that each of the generator, wind power generator, has this type of control structure with many PI controller and the synchronization unit. And if we look at the high voltage direct current transmission system, since we see that there is no generator directly connected here at this point, no synchronous generator. So we need to supply the AC voltage through this converter. So this converter behaves like a voltage source to this bus. So we also need a control for this converter. And if we see, this is one of the standard control. We have the inner loop current control, and we have the outer loop AC voltage control. So we have the many control system here to integrate the large amount of wind power. So what we see that we can connect wind power directly through the transmission system is shore if the distance is not very long, and if distance is very long or offshore wind power, we need high voltage direct current transmission system. Since it has many controller, and they introduce interaction among the controller. For example, this wind power controller, it can interact with the controller of the high voltage direct current transmission system. It also can interact with the grid, since the grid has many components, and grid has the different impedance frequency response. So this control, they can also interact with the grid. As a result, it introduced instability problem and introduced harmonic and oscillatory subsynchronous oscillation problem in the grid, like this one. Even if we have, when we design each of the wind turbine, and we assume that they are connected to a strong grid, they works fine during the design stage. When we connected many of them in a layout and try to connect them, and we can see that there are some subsynchronous oscillation or harmonic problem in the system. Some of the example of this problem is for example, now offshore grid. During the design stage, they see that they has 20 hertz oscillation in the system, and they don't know what is the reason, and they are struggling to find the source of this 20 hertz oscillation. And it's also same thing happened for Texas Panhandle in the US. It was also a very big wind power system, which is far from the Texas main grid. And they also see some subsynchronous oscillation. And they're working a lot to damping out this subsynchronous oscillation and proposing some new technique, expensive technique, to remove this oscillation. And another example is the Borwind one in Germany. And they plan for some repairing in the system. And when they shut down for the repairing or some maintenance purpose, and they want to restart, and they see that they cannot restart the wind power system, and it was connected through the SPDC system, and it's remained shut down for a year actually, and they were unable to identify the main source of the that preventing this restart. So many things happening. It's some example, but when you have the more wind in the system, then you can see that more problem can appear in the system, and they could be because of the interaction among the controllers with the grid and the impact of the interconnected system impedance. For example, we know that the current standard for renewable energy or the distributed generating unit like wind and we try to keep the short circuit ratio. There's the strength of the grid. We try to keep the short circuit ratio around 10. But when you have the many more renewable energy, then it's not possible to keep the short circuit ratio 10. So it reduces a lot, and this means the grid impedance is much higher. So they can interact with the grid. And other causes, some unidentified causes. So we need to study more to identify source of this oscillation. We need to do a lot more study to find the source of this oscillation or instability or interaction problem, how we can mitigate this. So those are some examples that I presented, that some real cases example. So if we need to install more wind power, and we need to do the pre-assess, like we have the simulation tool, different software, and we can do the simulation there. But we don't know. We can see from the simulation tool that the system is not stable here. But if we cannot do analytically, then it's very difficult to understand or to find the main source of the oscillation. So we need to understand it more clearly by different methods and tool and analytically. And we need to pre-assess their impact before connecting them to the grid. So we focus on to identify the causal relationship between this converter control algorithm and the grid, with the purpose of establishing design guideline that can guarantee the system stability. So we follow different approaches. For example, when we do the small signal analysis, they can be done with a different domain, like a frequency domain and the time domain. In the analytically, we mainly focus on the frequency domain to identify the source of the instability. Here in this presentation, I'll focus on two methods. One is the eigenvalue-based method, and the another is the impedance-based method. And the different method, when we design a control loop for a converter, then we just use a loop transfer function. We have the control. We try to determine the closed loop of the system and check whether the closed loop operate stably. And we design based on the step response and the load locus, all the things. But what is the main problem is that with the open loop or the closed loop design of the control system is that it doesn't consider it doesn't count the impact of the grid impedance or other component in the grid. So that is one of the main disadvantage of using only the open loop transfer function. We need to integrate the other method, like if we start with the state space modeling and the eigenvalue analysis, we can find the source of the instability. We need a more detailed analytical model of the system, and we can find the eigenvalue. And if we see any unstable eigenvalues, then we can perform the participation factor analysis to identify the source of the instability. So we can use the state space modeling, but the main problem is that it requires in detail analytical modeling of the system. Sometimes, for example, if we get a system from a manufacturer, and it might not be possible to have the internal structure of the system due to the industry secrecy and confidentiality. The other method is that impedance-based method. Impedance-based method can be applied with the analytical modeling on also by measuring the impedance in the terminal. So if we use just measuring the impedance of the terminal, then we don't need the analytical modeling of the converter. So this is one of the method now widely used to analysis the stability analysis of the power electronic system. And the other method is the nonlinear method. We will not focus on that because it needs much computation effort to analyze the stability of the system. So now we start with the state space modeling and the eigenvalue analysis. How we do the state space modeling and the eigenvalue. We have a system, wind energy conversion system or the SPDC system. We first try to find the nonlinear state space model of the system. So we try to first differential equation. We present the whole system through an ordinary differential equation. This is the nonlinear differential equation, and we know that we cannot apply this nonlinear equation to analyze the stability of the system. We can use the nonlinear model, but it's difficult. So what we do, we linearize the a small signal model around an operating point, and we come into a small signal model. The nonlinear model is easy to analyze for a simple system, but if we have a very larger system with a lot of step variable, for example, it's a 40 step variable. So what we do, we linearize the system around an operating point, and then we calculate the eigenvalue of the system. I'll show one example here, like a converter. What we have in the converter, we have a filter inductor in the AC side, and we have the capacitor, and we could have the transformer, or we could have another filter. Since they are three-phase system and it's a sinusoidal system, we cannot linearize the sinusoidal signal around the operating point. We cannot do it. What we do, we convert them into DC component, applying converting them into DQ system. So we have the VC system in the stationary frame, and we convert them into DQ rotating frame. Then each of the inductor here, ABC2, that come into DQ. So we got the two equation for the DQ inductor here, two differential equation. One is the DIT, DIQ, and similarly you get the two for the capacitor and the two for this other inductor here. And if you have the DC capacitor, and we got one equation for the DC capacitor. And if you have the transmission line, the transmission line can be represented in many different ways. This is one of the simplest representation through pi equivalent transmission system. So there are other methods also to represent the transmission system is in different diagram. So these are for the mainly passive parameters, but we have the controller here. So this is one of the example controller that we are using for wind power system. But we see that here we have the proportional and integral controller. So each of the integral term here introduce one differential equation. So we have the other differential equation for each of the integral, and we have the also PLL. So we need to have all the differential equation. An example of the state space model after linearization, and what we see here, this first four, these two states is for the capacitor, and these two are for the inductor. And here gamma LD, gamma LQ, and these are for the controller. So in the previous figure, we see that we have the current controller, and these are for the current controller. And we have also other controller like DC voltage controller. Here, rho DC is for the DC voltage controller. And we could have some filter. For example, this BPLL and is for the filter that we have, and this delta theta is the state for PLL. So we represent them in the state space form and linearized those. And linearize those, and then we get this a matrix. This is a matrix for one of the converter, and the B matrix for the same converter. And then we can analyze the stability from this state space modeling. Before that, before analyzing the stability of the system, we need to make sure that our analytical model is correct. So we try to verify the analytical model with one of the model built in the MATLAB Simulink with associational sim power system. Here, this is the validation. You can see the red line, a red dashed line actually here, but it doesn't look red dashed line. It took red line. You can see if you compare with the blue line, they are more like the same for all the three figures. Here we compare analytical model, the state space analytical model we tried with the switching model of in the MATLAB, and we see that this gives the same result, same dynamics, both the analytical model and the simulation model. So this one is for the benchmarking comparison that our analytical model is correct enough to study the stability of the system. If we don't see the same response here, like this one here, we see the very close match. If they are not matching very closely, this means that our analytical model is not good enough to study the stability of the system. So once we have the state space modeling and we have the matrix, and then we can study the stability of the system. So this is one example of a stability analysis. Here, the eigenvalues of the system, and it's presenting for the eigenvalue obtained from two different systems. Here, the star is from the analytical model that we derived a state space model, and here the circle is from a simulation software like the Dig Silent Power Factory. Dig Silent Power Factory has the option to calculate the eigenvalue from this software. So once we verified our analytical model by time domain simulation, and we see that our model is good enough to capture the instability of the system, and also we try to compare the result from the result obtained from a simulation software. And we see that the software, it was modeling the RMS modeling, it neglects some of the component. We do the participation factor analysis to identify each of the eigenvalue related to which state variable. For example, here, these two eigenvalues that we see, they are related to the control of the current controller, related to the current controller of the converter of a back-to-back system. And this eigenvalue is related to the DC voltage controller. So we can see that different eigenvalues is related to what? For example, this one is related to PLL. So once we know this eigenvalue related to, associated to which variable, then if any of them goes to the right-hand side of the of this complex plane, if anything here right-hand side, then we try to modify the gain of the system to bring back to them left-hand side. So we have the state space model, and we validate the correctness of the model in the time domain simulation, and also compare and then apply the participation factor analysis to identify which eigenvalue associated to which variables, and then we can perform the more analysis by changing the different gain. For example, this is the trajectory of the eigenvalue analysis. So if we change one of the controller gain of one of the component of the wind energy conversion system, and we can see which direction they are moving. For example, here this is the one of the case that is moving to the right direction, and we don't want them to move to the right direction. We want to go to the left direction. And after certain is related to PLL, I think here, and you see that if we increase the bandwidth of the PLL and some of the eigenvalue, they move to the right side of the layer of the figure, and this means it bring the system become unstable. So we can tune the parameter and change anything based on the eigenvalue analysis. So this is the one method that you can use to analyze the stability interaction of a wind energy conversion system. And one lacking is that we need a very detailed model of the system. So sometimes I said that we know that perhaps if we get something from industry and we do not know what it has inside, what kind of control, what kind of analytical model it has inside is unknown for industry, for academic people, or for the people who are using it. So that is the one main lacking for using a small signal stability because of needing this analytical model. So we can also do the stability analysis using another method like the impedance-based stability analysis for such system. How we can do the stability using the impedance-based system. So we have the converter, and this is the grid interface here. This is the grid, and we split the converter into two subsystems. One is called the source subsystem. For example, here the grid we can represent as a source, and we have the converter. I can represent the converter as a load. If we have the two subsystems, then we can represent through like this. One is the source as a Thevenin equivalent source with a series impedance, and we have the load impedance. We can also present it as a Norton equivalent impedance here, the converter. But for now, I am presenting that we represent the source as a Thevenin equivalent, and the load is a load impedance. Then if we want to see the voltage at the point of common coupling, common interface, and you see that the voltage at this interfacing point is like this equation. And what about the second part of this one? Here, this part can be represented through this equation. Here, G is 1, and H is the ratio. Here, ZS is the source impedance, and the ZL is the load impedance. So if you look at this equation, is the closed loop equation, is a transfer function of a closed loop equation with the forward gain unity, and the feedback gain is the impedance ratio. And we know that we can analyze the stability of the source system from the open loop gain. So we have the open loop gain. This is the open loop gain, which is that is the impedance ratio, the source to the load impedance ratio. So it gives us the stability if it meets the Nyquist stability criterion. So we can apply Nyquist stability criterion to this, whether it meets the Nyquist stability criterion. Based on that, we can say that the system is stable or unstable. So now I have to focus the stability for a wind energy conversion system. And we know that the wind energy conversion system, now we use there mainly a three-phase wind energy conversion system. So what we have here is a three-phase system. If it's three-phase system, then the impedance ratio matrix, this is the impedance ratio, is now it's not the single input, single output. It's the multiple input, multiple output. So what we do, we can either do the analysis based on the sequence impedance, the ABC that we convert into positive, negative, and zero sequence impedance. Then we can apply the stability based on the Nyquist sequence impedance. And it will be look like something like this one. Here, ZSP actually. ZSP and ZLP, P, or P, it should be P and positive and negative sequence. So we'll have the minor loop gain, LP and LM, and they are decoupled here. Since they are decoupled component, so we can apply the Nyquist criteria to understand the stability of the system. And if you see the control for a wind energy conversion system, we widely use the vector controller, the DQ frame controller, and it's not straightforward to calculate the impedance also in the sequence domain, since some component here they are in sequence, but the controller in DQ. The other way of calculating the impedance in the DQ domain. So we try to calculate the impedance in the DQ domain. when you calculate the DQ domain impedance, is we have the voltage VD, PQ, and the current ID, IQ. That give us the ZS source impedance is a 2x2 matrix, and the load impedance is also a 2x2 matrix. So we have the 2x2 matrix, and when you multiply them, this matrix, then it comes like this form. The minor loop gain is a 2x2 matrix. So the CISO, the single input, single output criteria cannot be applied here. So we cannot apply the Nyquist stability criteria directly. We apply here, it's called generalized Nyquist stability criteria. So we apply generalized Nyquist stability criterion. And what we do, we have the two eigenvalues here, the lambda 1, here 1 lambda, the other. And if we solve this equation in the frequency domain for different frequency, that gives us the eigenvalue lossy of this system. So now we can apply impedance-based analysis either in sequence domain or the DQ domain. In this work, I will present the analysis based on the sequence domain, based on the DQ domain impedance. So now we have the controller, DQ frame controller. We try to obtain the impedance, analytical impedance model of the system. We have the control dynamics, and this controller, they have a very good impact on the impedance of the system. We try to obtain the analytical model of the impedance of this wind energy conversion system. And we come to this form. This is the one of the form. Maybe I presented some reference somewhere here where we present the detailed analytical model of the system, how we can obtain the detailed analytical model of the system, the step-by-step process to obtain this model. But how we can ensure that this analytical model is correct? So we need to verify this analytical model. We build this converter in MATLAB Simulink, for example. This also can be done experimentally. And we inject some different frequency signal here at this terminal and let them to enter to the converter. So since they are the different frequency current signal with a low magnitude around 5% to the operating point, this current also produces the same voltage signal. And this voltage divided by the current, we get the impedance. So we can see this is a validation here. The solid line, you can see one blue solid line is from the analytical model, from this equation that we obtain. And you can see some of the dot line, some of the dot, and this from the measurement in the simulation. So we see that our analytical model is correct enough and is overlapped with the simulation model. So that tells us that the analytical model is correct. So once we obtain the analytical model, then we don't need to do simulation to study the stability. Then you can do analytically the stability of such converter system. One example here, you can see that we know that since DQ domain impedance, so we have the two eigenvalues. Since a 2x2 matrix that give us two eigenvalue, and from the generalized Nyquist criteria, if one of them encircle this critical point -1, 0, 0, 0, then the system is unstable. So for this application, we see that for this one, we see that it doesn't encircle. This means the system is stable here. And we changed the controller again. One of the example here, like the current controller, and what we see that it encircles the critical point. This is the zoom view of this part, and we see that the blue one encircles the critical point. For this one, we see the simulation result is very good. It doesn't have any instability problem. But when we change the controller again and how the simulation result look, you can see that when you change the gain somewhere here online, and you see that the system is no longer stable. So now we can analytically verify that the system is stable or unstable based on the analytical result. It also can be now possible since that when we connect the wind power, and it's not possible to have the a strong grid. The grid can be very weak. For example, here we have the short circuit ratio of the grid is 5. It's good enough. We see the system is stable. But when we reduce the short circuit ratio of the grid, we make the grid weak by increasing the impedance or having a very long transmission line that make the grid weak. And we see that for weak grid, the system can be unstable. So now you can play with the different components of the system to make the system stable analytically. Once it's stable in the analytically, then you can verify it also in the simulation. And then we can go for real implementation in the system. So this is more about a single converter, single wind energy conversion system, let's say. And if we want to integrate them through the high voltage direct current transmission system, then you have the converter. We can represent the whole wind farm here up to this point. So we have the whole wind farm, and we know now impedance model for each of the wind farm, each of the wind turbine. As we know, we need to also derive the impedance model for HVDC converter system. We have the controller, then we need the analytical impedance model of the system. Of course, it needs to be also verified. And then we can represent through an equivalent model. So the whole wind farm, all of the wind turbine, they are connected either in parallel, in series, so we can write the equivalent impedance model of the system. And from this bus, the SA collection bus, we represent as an ortho equivalent. We have the equivalent wind farm impedance and parallel with the current source. And this HVDC system, we are representing through a Thevenin equivalent. So that gives us also the same closed loop gain. Is a closed loop transfer function with the forward gain unity, and feedback gain is the impedance ratio. So we can analyze the stability for the system. So one of the example here, before doing the stability analysis, we just try to connect to one peak wind farm through the HVDC system. And what we see that we have the some sustained oscillation is 15 hertz here. We have the fundamental frequency 50 hertz, and we have the 15 hertz. So this is the 15 hertz. Since is reflected to the fundamental frequency 50 plus minus 15. So this gives 65 or 35 hertz oscillation in the sequence domain. So this 15 hertz is reflecting in the fundamental frequency plus minus 15. So that gives us, we see that we have this 35 and the 65 hertz oscillation in the sequence voltage. So how we can get rid of this voltage? We can do the stability analysis using the impedance space analysis for the condition that we see the system is unstable, and we check that the system is unstable. This is the Nyquist plot, looks very complex, but when we look at the impedance, we see that there is a crossing at 15 hertz, and we don't have the end of phase margin at that point. So that making the system unstable. So using the impedance space analysis, we can get how we can analytically identify the system stability. Then we can propose different method to solve the instability. We can either change something in the wind farm or in the HVDC system, or maybe somewhere in both. We can do many things to change to bring it back to a stable system. This is an example where we change the controller bandwidth. This one is for the HVDC system, where we change we increase the faster. We change the control loop, the AC voltage control loop, make it more fast in these two cases. And we see that it doesn't encircle the system. So the system becomes stable if we increase the bandwidth of the AC voltage controller. The other way also, we decrease the bandwidth of the wind energy conversion system. That's also make the system stable. And this control bandwidth depends on the switching frequency, of course. We try to keep the outer loop 3 to 10 times slower than the inner loop. And this bandwidth is limited by this switching frequency, inner loop and outer loop, also with the PLL. So it's not always possible to change the bandwidth because of many reasons. But this is the one way of stabilize the system. Here, this is another example where we change the PLL bandwidth. We see that as fast the PLL, the performance is better, but for the weak grid, it brings instability in the system. So we try to reduce the PLL bandwidth. That's also bring the system more stable when you have the PLL. So this is the one of the case that where we see the system stable for changing the control loop bandwidth, and we see the Nyquist plot. This is the generalized Nyquist plot, of course, and it doesn't encircle the point here anymore. If it doesn't encircle the point, this is a time domain simulation, and we see that before we have this 15 Hertz oscillation, now the 15 Hertz is gone. We don't have this 15 Hertz oscillation anymore. The other method for improving the stability using damping, we introduce an active damping. What we do, we have this 15 Hertz oscillation, and we try to remove, we try to introduce the controller here that produce the 180-degree phase shift of this 15 Hertz. So this is the additional signal that we introduced, which is 180-degree shifted of the original oscillation. So actually, we are producing some oscillating signal, this 15 Hertz, and it cancels each other. So that when it cancels each other, then it produces the then in the system we don't see the instability anymore. And we also check what is the impedance frequency response with this damping, and we see that here the green one is with the damping. Since the converter here, the HVDC converter is operating as a source, and we know that as low impedance in the source is a better, stability is better. When the impedance is higher, this means it's a weak grid. So introducing the damping, it decreased the impedance at the low frequency. So it improved the stability performance. That's what we see here. So this one is with the active damping. And if we see now with the impedance frequency response, before we have crossing here with the magnitude at 15 Hertz, now we no longer has this 15 Hertz crossing here anymore. If we don't have this 15 Hertz crossing, and if we check the Nyquist stability, and we see that it's not crossing anymore. It's not encircling this point anymore. So this is the another method for improving the stability of the system. And I was talking about the. So I was talking about the black box system, for example, here we have the wind farm, and this wind turbine generator, they can come from different vendors, different company, and the HVDC, they can also come from different vendors. But how we can analyze the stability of such system, since we don't have any information about the wind energy conversion system, the vendor, the manufacturer, they usually don't provide what it has inside. So it's also same for the HVDC system. We don't know what it has, what it has inside. So how we can study the stability of the system, and if we see any interaction problem among them, how we can analyze the stability. So one way we see that we measure the impedance here, each of the component, and try to extract what it has inside the control system. So we develop a method. Even though this wind energy conversion system, internal structure of the wind energy conversion system, I mean the control structure, is unknown, but we develop a method that tell us what kind of control it has inside and what is the controller parameters there. So once we know what kind of control it has controller it has inside, and the control parameters also, if we know that, then we can easily apply the impedance-based stability analysis. So this is one example that even though the internal controller structure is unknown, but we can try to identify what kind of controller structure it has and what is the bandwidth of the system. This is one of the interaction problem that we see that for this particular application, we see 8.5 Hertz oscillation. And when we apply the impedance-based analysis and we identify what is causing this interaction problem here. And we see that we first identify what it has internal structure, and it can be replicated in the simulation model, the analytical model, and now it can be try to change the different parameters there. And then that can make the system stable. More detail about this can be found here in this reference. We discuss in detail about this, and we see also recently some other works that also follow this work to find the critical parameters in a system following the method that we propose. Then we can stabilize the system, using the method. So these are some stability issues that I discussed, and what other issues apart from this interaction problem. And we see that we have the inner loop control, outer loop control, and the PLL. So many control they are cascaded, and the bandwidth is limited. So that is the one limitation that what we see with the current controller, standard controller structure. And the other is that they are injecting the power coming from the wind, injecting directly to the grid, regardless of the condition of the grid. So that is the one big limitation. And they do not comply with the grid code. This means when you have the traditional generator, they participate in regulating the voltage and frequency. But the standard generator control system now we are using, they do not participate in regulating the voltage and frequency. So we need to have some different control that can regulate the voltage and frequency. And also another thing is that this control needs a communication. And when you have the million of converters, such converter in the system, it's very difficult to, maybe it would be impossible to maintain the communication among the converter, or it's inside the controller. So we need to find alternate controller. One example of such system is the sync converter, and this controller structure here is developed based on the synchronous generator, theory. And another, maybe I should, we don't have that much time, so I should give some time also for question, perhaps. So use the synchronous generator theory to develop this controller structure developed by Professor Jong, and we applied it for a back-to-back conversion system. And for a standard controller, maximum power point algorithm, tracking algorithm is implemented usually in the rotor side converter. But here we move the maximum power point tracking algorithm to the grid side converter. so that it can regulate the voltage and frequency of the grid. So we shifted the maximum power point tracking, and we tested it for one generator, one converter system, and we see that the performance is really good with this control system. But one limitation we noticed with this, it doesn't have any internal controller, current controller. So is there any fault or anything happened that it cannot limit the current? So that is one of the disadvantage of this control. Otherwise, we see that this control works and its performance is very good in terms of regulating the voltage and the frequency and minimizing the communication in the system. We also tracked the impedance-based analysis with this control. And if you compare the impedance characteristics for this controller, sync converter, and we see that it's like an RL. So more like a synchronous generator behavior. While if you use the standard controller, then the impedance characteristics is more complex. Here, the circle, pink and blue is for the standard control, and the green one is for the synchronous generator control. And we discussed more detail of this in this paper. And so we see that it has some better properties. And we tested the system for a very large system. Texas Panhandle is a large system, and we see that for a standard control, if we use the standard control, and it can send the power up to 80% of the rated generation of the system. If we go higher than 80%, the system is becoming unstable here. Here you can see this is the instability for a standard DK controller. But if you use the sync converter based controller, and you see that the system is now can send power up to 100%. So this is the one advantage that we see. So now I should go to the concluding remark, and in this presentation, we look at the possible origin of the subsynchronous oscillation in stability. This is the main focus, and also the interaction among the controller with the wind energy conversion system and the HVDC converter. That is we discussed it, and also the impact of the interconnection system impedance. That is the grid impedance. What is the impact of this? And also we discussed the role of the source to the load control loop bandwidth ratio and how we can retune the control loop bandwidth to make the system stable. And we also proposed an active damping to minimize the instability problem. And alternatively, we checked the alternative control like the sync converter, or another one is the droop controller. Sync converter or the droop controller, they can also give the better stability properties. And we need further effort to understand the interaction, or we need even more advanced controller to minimize the interaction to have a more robust integration of the renewable energy. So thank you all. That's what I have to present today, and maybe it's a time for some question. I'm sorry that I don't keep enough time for the question. Thank you.
Yes, thank you, Dr. Amin. It is a very nice presentation, and almost you have covered total wind energy system with issues and control aspect, how to improve the stability, and how to analyze the stability also. You have gone through the this one also, virtual inertia concept and eigenvector analysis. It was really very much impressed, what I can say. And if any of the participant is interested in this, particularly in the wind energy conversion system, definitely it is a valuable and very useful talk and definitely they will follow all the publications what you have also given here in this PPT. Yeah, thank you, Dr. Amin, for your valuable talk. And I will ask if any participant having any kind of small queries, they can
thank you.
share.
Yeah, thank you. Yeah.
Yeah, they can unmute and they can directly ask also.
Yeah.
Good afternoon, sir.
Yeah. One by one. Can you introduce first?
Good afternoon. I am Habibur Rahman Ansari.
But otherwise it's
yeah.
coming.
Good afternoon. I am Habibur Rahman Ansari. Sir, I am having one question. What are the various methodology with the help of which we can improve the voltage stability of wind integrated power system?
Voltage stability.
Is asking the question like this, how to improve the voltage stability in case of a wind energy conversion system? What may be the methods?
Yes, thank you, Habib, for your question. It's an interesting question. I can share one of my experience when we are studying the Texas Panhandle wind power system. And we see that if we have a standard control, they usually do not participate that much on regulating the voltage. So voltage instability occurs because of the reactive power control actually. So if we have the reactive power controller implemented with the wind energy conversion system, and they can inject or absorb the reactive power depending on the voltage condition, that improves the voltage stability of the system, like the virtual synchronous machine, and it can absorb or it can produce reactive power to regulate the voltage. If we regulate the voltage, then it will improve the voltage stability of the system. So in conclusion, I can say by regulating the reactive power of the system, we can control the voltage.
Yeah, thank you.
And
thank you very much.
And the other method is that, for example, some of them are saying to install synchronous condenser, like a synchronous machine operating without any load, or maybe FEX devices or the custom power devices, the voltage regulation. They can also be installed, but if we have only the voltage regulation with the control itself of the converter, then it improve the voltage stability of the wind energy conversion system. Yes. Thank you. Yeah.
Thank you, Dr. Amin. Hopefully there is no more questions. And,
good afternoon, sir.
Yes.
Sir, it is Nidhi Saujani from Government Polytechnic, Rajkot, Gujarat.
Yes.
Sir, I want to ask, sir, which software will be helpful if I want to address protection issues with DG integration?
Sorry, could you repeat one more time?
Sir, I want to study protection coordination and all that, protection issues while DG is integrated. Okay. Yeah. So will you suggest any software for that?
Thank you for the question. Particularly, what
may I interrupt here because sir has delivered particularly on stability as well.
Stability. That is why my topic is different, and that is why I especially ask her if he may answer, if he may suggest.
Oh, yes, okay. Suggestion. It is one kind of suggestion. If you have any idea that what kind of software can be useful for protection.
Yeah.
Thank you. Thank you for your question. And of course, it's an interesting question. I agree. When we develop the control system for a converter for a particular wind energy conversion system, then this is the power electronics converter. We have the controller. We try to implement its own protection system, like over voltage and the over current, all the protection system. We implement this protection system inside the software. When you write the software for the DSP or the microcontroller or in the FPGA, we try to implement this control system in a protection system for the converter. And when you design the hardware, like in this after the signal conditioning circuit, you also implement the control. But I think U1 is the more like is the stability of the grid system, of the grid protection system, like wind power, and we have the grid. I think might be Dick silent power factory could be one that can be used to analyze this this protection. And the another one, it could be MATLAB simulating association with sim power system that can be used to analyze the instability, the protection system of such DG integration. So it depends on whether you want to focus on one DG or a cluster of DG with the large system. So it also depends on that.
Okay,
Yeah,
sir, probably I
thank
would
you.
like to integrate more than one DGs. So DG silent factory will be more helpful, right? According to you?
Yeah, it's also
Madam?
and also MATLAB simulating association with sim power system.
Okay.
Yeah,
And
madam,
sir,
I will be adding to your question answer.
yeah, sir.
You will go with the PSS software.
Yeah.
That will be much more useful for protection. One of
Actually, sir,
our
I am confused with PSCAD and DG silent factory.
No,
So
PSS software is much more flexible, and you can go for the number of DGs, multiple DGs. And one of our faculty here, particularly Dr. Sheikh Afizullah, he is working in that particular area. If you have any kind of resource problem or any difficulties, you can interact with him.
definitely, sir. Thank you. Thank you so
He
much,
is
sir.
having few research articles in that protection areas particularly.
Thank you. Thank you, Amin, sir. Thank you, sir.
Yeah, thank you, Professor
Thank you,
Gader.
Dr. Amin, and we will conclude the session here itself.